Hello students, welcome to EPG Pathshala. I am Professor Devendra Mohan from Guru Jambeshwar University of Science and Technology, Hisar, Haryana. Today we are going to discuss the module Ruby laser, Q switching and mode locking from the paper Atomic, Molecular and Laser Spectroscopy. We will be able to learn Ruby laser and its working, energy level diagram of Ruby laser, production of giant pulse with the Q switching mechanism, Kerr effect, peak power emitted during the pulse, mode locking and mode pulling. We will be able to learn Ruby laser and its working, energy level diagram of Ruby laser, production of giant pulse with the Q switching mechanism, Kerr effect, peak power emitted during the pulse, mode locking and mode pulling. Ruby laser is the first laser emission using ruby crystal, which was demonstrated by T.H. Memon in 1960. Ruby is known as sapphire with a small percentage of 0.05% of chromium ions, replacing aluminum ions in aluminum oxide Al2O3, also known as alumina. The chromium ions impart pink color to the ruby and are responsible for the emission of light by ruby. Working of a ruby laser. The active material is a cylindrical ruby rod which is around 0.8 cm in diameter and 15 cm in length. The ends are flat to better than lambda by 10. The cylindrical surface of the rod is grounded to prevent total internal reflection. The optical pumping mechanism is used for creating population inversion. It is in the form of helical xenon discharge tube and the ruby rod is placed at the axis. The little part of pump energy is used to excite the atoms and the rest generates heat and hence cooling is required, for which the circulating water arrangement is made. Resonant cavity is made by fully reflecting plate at the left and partially reflecting at the right. The ruby laser is commercially available in both pulsed and continuous wave laser depending upon the optical source of pumping mechanism. In ruby laser, energy levels are those of chromium ion and it has two main pump bands 4F1 and 4F2 centered at wavelength of around 0.55 micrometer, which is green, and 0.42 micrometer, which is violet, respectively. Each pump band is around 1000 angstrom width. The metastable levels split up into two sublevels, 4F1 with a separation of delta E is equal to 29 cm inverse. The xenon flash lamp provides a flashlight of 5600 angstrom, while other flash lamps give 0.42 micrometer to 0.56 micrometer. The figure depicts the energy level diagram of ruby laser, wherein it is mentioned that 4F1 band and 4F2 band and metastable state and the ground level state, and the main emission of ruby laser is at 6943 angstrom. Although there is a violet emission at 0.42 micrometer, but the most commonly used is 6943 angstroms. The lifetime of pump band is of 10⁻⁹ second and that of metastable band is of the order of 10⁻³ second. The ruby rod is placed inside the xenon flash lamp. Flash lamp and ruby rod coincides with the focal line of cylindrical reflector. The energy from flash lamp raises the atoms to the pump bands and these decay to metastable band via non-radiative transition. The population inversion is achieved in a very short time as the metastable state gets highly populated and the atoms from metastable band decay to ground level, emitting the radiation of wavelength 6943 angstrom and 6929 angstrom. The lines are separated about 14 angstrom. The ruby laser is a three-level laser system. The photons traveling along the axis of cavity are reflected back and forth and pass many times through the amplifying medium and it is worth noticing that the photons traveling in any other direction would be lost after a few reflections, and the output power of commercially available ruby laser is 100 joules per pulse, and a pulse lasts for 10⁻⁻⁷ seconds. Production of giant pulse, Q switching. The flash lamp operation gives rise to pulsed output of laser emission. During the time flash lamp doesn't operate, population of upper level is depleted at a very fast rate and the lasing action doesn't occur till the arrival of next flash from the lamp. However, the output consists of high intensity spikes of approximately 0.1 microsecond to 1 microsecond duration. This phenomenon of spiking is due to laser transitions at a faster rate at threshold flash lamp power. In this way, the laser operation stops and starts depending upon the rain inversion of population inversion at next flash lamp power. Hence, a series of pulses is produced while we require that the maximum energy is concentrated in a single pulse of very short duration. The technique of producing a very short intense pulse of light is known as Q switching. It is called Q switching because the technique involves switching the Q factor from a low to very high value of the resonator or the cavity. So basically it is Q factor of the cavity. It is closing of the optical cavity by any means until the population inversion is built up much above the threshold and suddenly opening the shutter, permitting it large fraction of energy to come out in a single giant short pulse. As mentioned, the output of a solid state laser, here we are talking about ruby laser, consists of 1 millisecond long bursts of spikes, each lasting for 550 nanosecond, and average spacing between spikes is about few microseconds. If a shutter is introduced in front of one of the mirrors, it will prevent oscillations to take place and active medium is continuously pumped. Then population inversion is raised much above the threshold level and then the shutter is suddenly opened. The energy stored comes out in the form of a giant pulse. If a shutter is introduced in front of one of the mirrors, it will prevent oscillations to take place and active medium is continuously pumped. Then population inversion is raised much above threshold level and then the shutter is suddenly opened. The energy stored comes out in the form of a giant pulse. The process changes the Q value of the cavity from very low value before opening to a very high value after opening. The output consists of a giant pulse if the shutter is opened in a shorter time than required for building of laser oscillations. Obviously, if shutter opening is slow, then output consists of series of pulses with less peak power. So the Q switching is a requirement to have a giant pulse. The following switching systems are used for Q switching. One is mechanical shutter. A fully reflecting mirror is made to rotate rapidly about an axis perpendicular to the axis of resonator so as to make it instantaneously parallel to the output reflector. The mirror is rotated with a synchronous motor and flash lamp is timed to fire so that mirror is parallel to the other reflector when population inversion is maximum. The other technique is electro-optic shutter. The function of electro-optical shutter is based on Kerr effect or the Pockle effect. Kerr effect. The degrees of alignment of some materials when placed in an electric field, the dipoles are aligned along the direction of electric field and also depend upon strength of the electric field. But there are some materials in which the molecules are not symmetrical, then the molecules are anisotropic and show birefringent character. In the presence of electric field of constant strength, birefringence, that means the difference between the refractive index of the ordinary ray and the extraordinary ray n naught minus Ne is proportional to the square of the field and to the wavelength. Therefore, the optical path difference between ordinary and extraordinary rays in a cell of thickness T is delta n is equal to k lambda E square, where k is referred to the Kerr constant and the value of k is 2.4 into 10 to the power minus 10 centimeter. The liquid is nitrobenzene, which is used in the Kerr cell. It is kept between two flat parallel plates spacing several millimeters. The potential difference applied between the plates is of the order of 10 to 20 kilovolt. Now the cell containing the liquid is located between crossed polarizers. It acts as a fast shutter known as electro-optic shutter. The direction of electric field is kept at 45 degree to the direction of polarizer axis. When there is no electric field, light is not transmitted. In the presence of electric field, the light passes such that n naught minus Ne L is equal to lambda by 4. And the Kerr cell acts as half wave plate in double pass and rotates the plane of polarization by pi by 2. The voltage necessary for this action is a half wave voltage. Now, coming to the peak power emitted during the pulse. If N1 and N2 are the populations of the two levels respectively, the total number N naught per unit volume is given by N naught is equal to N1 plus N2. Then normalization gives us small n1 is equal to n1 by n naught and n2 is equal to n2 by n naught, so that n1 plus n2 is equal to 1. The single pass gain of the laser rod is given by G is equal to exponential sigma naught n2 minus n1 into L, where sigma naught is the absorption cross section and the quantity n2 minus n1 is the normalized population inversion. Now suppose the normalized population inversion is Ni before the shutter is switched on and at the end of the pulse it is Nf, then the total energy emitted during the pulse is E is equal to 1 by 2 Ni minus Nf into N naught V H cross omega. Here we have taken V as the volume of the active material, and the factor half has a significance that the population difference changes by 2 units every time a quantum is emitted. The duration of the Q switched pulse is estimated from the decay of the pulse in a cavity. If L is the length of the cavity, then time taken by the pulse to make a round trip is given by T1 is equal to 2L by C, and each time the pulse strikes the mirror, it loses 1 minus R of its energy, as R is reflection coefficient of the output mirror. The fraction of the energy lost in unit time is therefore 1 minus R by T1. Hence the cavity lifetime Tc can be understood as Tc is equal to T1 by 1 minus R. This is the delay time of the Q switch pulse, which has a full width of about twice of Tc. For a nearly triangular shape of the pulse, one can estimate the peak power of the pulse using the relation P is equal to E upon twice of Tc. Mode locking. Mode locking is a technique by which ultra short pulses means picosecond or femtosecond pulses are generated in a laser. The output of the Q-switched ruby or ND-YAG laser consists of a pulse of duration over a range of 10 to 100 nanoseconds, which is very short and results in outbursts of very high power. If the laser gives average energy of 1 joule and the pulse time is 20 nanoseconds, the average output power comes out to be 50 into 10 to the power 6 watts. That means 50 megawatt, too much of the power. These pulses of nanosecond duration overlap, thereby making pulses of even shorter durations of the order of 1 to 10 picoseconds. Pico means 10 to the power 12 minus 12 seconds. Mode locking can be done by active mode locking and passive mode locking. There are figures which shows that how the mode locking is done in ruby laser. There is a cavity arrangement for mode locking. Basically, the die cell is kept as the Brewster angle. and there is a coupling of the lens, and the figure depicts that how the arrangement is made for mode locking purposes. Mode pooling. It has been established that a number of axial modes separated by resonate within the Doppler broadening line width of a given atomic transition. This was experimentally verified by Harriot in 1961 and later by Bennett in 1962. There were some interesting anomalies revealed by Bennett's experiment. He found that the beat frequency is not equal to but is less than by about 1 part in 800. Firstly, the frequency of the C by 2L beat increases with increasing power. This increase was anomalous. It is expected that the pulling is towards the line center to increase with the number of the excited atoms, and the pulling would be less for a cavity resonance near the line center than for one further away from it. Hence, the frequency separation between adjacent cavity resonances should decrease with increasing power. Secondly, at low powers, a single beat was observed at just less that with the increase in laser power, the 20 kHz and the beat appeared when the power was further increased. The beat became triple and the beat double, and so on. In a passive resonator, the separation of the adjacent frequencies of the modes is given by delta omega q is equal to pi c upon L in an amplifying medium, and the equation modifies to delta omega a is equal to pi c upon Ln, where n is the refractive index. And now for W less than W naught, NW less than NW naught, and hence increases. So that is the frequencies on the left of W naught which move to the right. On the other hand, frequencies on the right of W naught shift to the left, because for W greater than W naught, NW is greater than NW naught. This implies that the frequencies on either side of W naught are pulled towards the center of the gain curve. Therefore, as the name suggests, mode pulling, since the frequencies on either side of W naught are pulled towards the center of the gain curve, therefore the concept is known as mode pulling. The phase shift per transit through an evacuated tube of the length L is phi is equal to WL upon C. Therefore, the dispersion for the evacuated cavity is curly phi upon curly omega is equal to L upon C. Now, the quality factor Q of the cavity is given by Q is equal to W into energy stored in the cavity divided by energy lost per cycle to the walls, which is equal to W oscillatory into E divided by C by L Fe, which is equal to W oscillatory divided by C by L into F. E gets cancelled, and the quality factor is also defined as Q is equal to minus of W oscillatory divided by delta W oscillatory. So, W oscillatory upon C by L F is equal to W oscillatory divided by delta W oscillatory. Therefore, delta W oscillatory CF upon L gives us curly phi upon curly W is equal to L by C is equal to F upon delta W oscillatory. The W average actual frequency of the oscillation is given by curly phi upon curly W, W average minus W oscillatory plus delta phi M W is equal to 0. So that W actual frequency can be written as W oscillatory minus delta phi M upon curly W is equal to W oscillatory minus delta W oscillatory upon F delta phi M W. And using the Kramer-Skroning relationship, delta phi M W average is approximately minus GW omega M minus omega upon delta omega M. Writing omega average from this, one can write down omega oscillatory delta omega M plus omega M delta omega oscillatory divided by delta omega M plus delta omega oscillatory. And in case of inhomogeneous broadening, the relation becomes delta phi M W is equal to minus 0.28 G omega exponential minus omega m minus omega upon 0.6 delta omega m square, sine of omega m minus omega upon 0.3 delta omega m. This mode pooling accounts satisfactorily for the observed axial mode beat of just less than, and also for the splitting of the beat when other axial modes start to oscillate as the input power is increased. It doesn't account for the power dependence of the actual frequencies between the beat components at pi c upon L and 2 pi c upon L. Now, there can be various questions that what are the advantages of using mode locking technique in lasers, and describing the role of the saturable absorbers, what is the quality factor of the cavity, and how the bleaching effect in the saturable absorber is advantageous for mode locking, and what do you understand by mode pooling. So, we had discussed all these things. What is the role of modulator in obtaining the mode locked pulses? The method used to obtain the operating conditions consists in using a rapid light modulator that can chop the light in the cavity into periods of exactly the same length as a round trip. This implies that only those photons allowed to pass through the modulator in its on state will be amplified, and will always find the modulator in this state after each round trip. The other photons elsewhere in the cavity will be subject to losses when they travel through the modulator. So, let us summarize that what we have learned in this model. We have understood the ruby laser and its working principle, energy level diagram of the ruby laser, production of the joint pulse, Q switching, Kerr effect, peak power emitted during the pulse, mode locking and mode pooling. Thank you.